it's the number of p coin tosses until your first heads. So sorry if I said that slightly wrong the last time. What I meant is x is the number of trials until your first success. So for example, x would take values 1, 2, 3 up to infinity possibly. And so if x is 1, you would get a head right away with probability p. If x is 2, it means you get a tail and then a head with probability qp. If it is 3, then it's tail heads with probability q squared p. So the geometric formula on 1, 2, and so on is q to the k minus 1p. And here it's important to understand that for geometric, every trial is independent. So we have coin tosses here. Today we're going to review student responses to the concept test from last time. We'll talk about the expectation of a function of several variables and look at the then we'll start section 3.3, which is SD variance and Chebyshev's inequality. So remember the concept test from last time. Consider a well-shuffled deck of cards, the expected number of cards between the first and second ace, not counting either ace. So it is 48 over 5. So one student, these responses were for finding actually the expected number of cards between before the first ace, but the reasoning is just the same as this follow-up question. So think of slots, so basically we have a slot before and between all the A's where the non-aces fit. And so every non-ace card has a 1/5 chance of being before the first ace or between any two aces. And we have 48 non-aces, so we're going to have a sum of 48 indicators, each with probability 1/5, giving us 48 over 5. One student who said C, said spread out aces over 48 non-aces means on average there should be one after every 12 theoretically, but actually it's 48 over 5, so it's 9.6. One person, interestingly, uses a geometric distribution argument, but gets the wrong answer because the expected value of geometric is, so in fact it's not 1 over p, it's 1 minus p over p, because this fact that it's 1 minus p over p, this is something we'll learn in section 3.4. And so, but there's a problem here with this application, which is why he got it wrong, besides just the fact that it's 1 over p. So here, it's a brilliant idea if you're trying to find the number of trials before the first success. Let p be the probability that you draw an ace. So the chance of that's 4 over 52. So if x is the number of non-aces before your first ace, and you want x to be geometric p on 0, 1, 2, and so on. So the problem is that, remember, geometric requires independent trials. And with our card question above, the cards are without replacement, right? So we have dependency there. So that's what's breaking down in his argument. But if you ignore that, the expectation of x is 1 minus p over p, which is 1 minus 4 over 52 divided by 4 over 52, which is 48 over 4. So interestingly, if the question had allowed for dealing the cards with replacement, the answer would have been 48 over 4, and our indicator argument would not have worked in that case. So now we're going to talk about expectation of a function of a random variable. So remember, expectation is defined as basically it's a weighted sum over all the outcomes in your random variable, weighted by the probability that that random variable takes that value. So the expectation of a function of x is the sum of running over all x's, g of x probability of x is equal to x. So let's see an example of this. So say if x is geometric p on 1, 2, and so on, with p greater than 2/3, let's find the expectation of 3 to the power x. So basically we have x on the left-hand side and 3 to the x on the right-hand side here. So our x's are 1, 2, 3, and so on, and with probabilities p, qp, q squared p, and so on. And on the right-hand side, g of x is 3 to the 1, 3 squared, 3 cubed. So our formula for expectation of 3 to the x is, so it's the sum over all of these outcomes. So it's the sum from k equals 1 to infinity, 3 to the k, probability that x is k. And when you work this out, you see that we have a geometric sum here. So you have 1 plus 3q plus 3q squared and so on, which is 1 over 1 minus 3q if 3q is less than 1. And 3q less than 1 is true because we assumed above that p is greater than 2/3. So the answer is the boxed formula. So then I asked you guys to work out if x is plus on 1/3 to find the expectation of x factorial. And again, you just use the definition of expectation of a function. And the beautiful thing is that the k factorial in the Poisson formula cancels, and you just have a geometric sum then, and it works beautifully. So we have this should be a 3 over 2, I guess. Great. So then if we want to extend this to several variables, so let's say we have a joint distribution, then the expectation of g of x, as we said, we sum over all x's, g of x probability x is x, so it shouldn't be that surprising that for multivariables we have expectation of g x y is, now we're going to sum over all xy's. We're going to sum over all xy's, and so here sum over all xy's, and so we take g of xy times the probability that x is x and y is y. So for example, if we have this joint distribution shown here, let's find the expectation of x, where we think of x as g of xy equals x. So we know the answer should be a half because we can see from the marginal here that it should be a half, and you can confirm that as we run over all x's and y's, we do indeed get a half. So we can confirm easily that the expectation of x plus y is the expectation of x plus the expectation of y, and I asked you guys to show that if x and y are independent, then the expectation of xy is the expectation of x times the expectation of y, and this again just follows from the definition and what it means to have independence, that the joint probability factors, and just some easy facts about sums. So we are done with section 3.2. Moving on to 3.3, the standard deviation is the average spread of your data around the mean. So, for example, in this picture where the mean is 3/2, you can see that the average spread should be around 1. It's 1/2 would be too small because we are getting some data values out around between 1 and 2 and between 5 and 6. And 2 is too large because most of our data is between 3 and 4. So 1's about right. Most of your data is between 2.5 and 4.5. So, but of course there are formulas for what SD is. So SD is so the deviation from the mean is x minus expectation of x. We square it. We take the average of that, and then we take the square root of it. That's the same effect as the absolute value of the deviation. And variance is just the square of the SD. So important application of this is Chebyshev's inequality, which, like Markov's inequality, provides an upper bound. So we have, for any random variable x and any k greater than 0, it says that the chance to be in the tails, in other words, to be more than k SDs from the mean, is less than or equal to 1 over k squared. So for example, in this picture, where the expectation is 35 and the SD is 15, the probability to be greater than 30 from the mean, in other words, less than 5 or greater than 65, is, so we see that k here is 2, because the SD is 15, and 30 is 2 times 15, or 15 is the SD, so it's less than or equal to 1 over 2 squared, or 1/4. If someone asked you, what can you say about the probability that x is greater than or equal to 65, because the distribution isn't symmetric, you can't divide that 1/4 by a half. The best you can say is that it's less than or equal to 1/4. So we have, if you want to, we have Chebyshev's and Markov's inequality. Chebyshev, if you have both the mean and the SD, you can compare what you can get from both of these. So Chebyshev, of course, gives you an upper bound for being in the tails, being more than k sigma away from mu. But you can also think of it as if A is mu plus k sigma. In other words, if I don't have that absolute value sign and I just bring mu over to the other side of the inequality, you'd get x is greater than or equal to mu plus k sigma, that is less than or equal to 1 over k squared. That's what Chebyshev gives you, and it doesn't require that your random variable be greater than non-negative. Markov does require you to be non-negative, and says that the probability that you're greater than a is mu over a, or if a is mu plus k sigma, then it gives you mu over mu plus k sigma. So sometimes you'll be wondering which of these is going to be better for you. Most of the time, Chebyshev will be better because of that k squared term will make that smaller than mu over mu plus k sigma. But in any case, here we did a concept test, and Markov inequality was better here because our average was 1 and our SD is 2, and we're finding the proportion over 5. So first of all, it doesn't follow a normal distribution, clearly, if the SD is 2 and the average is 1. The Markov inequality would give you less than or equal to 1 over 5. Chebyshev, I recognize 5 as mu plus k sigma, so k must be 2. So this is less than or equal to 1 over 2 squared, or 1/4. So I can see that Markov is better. Great. So we'll continue with this next time. Have a great day.